Well, welcome everyone. My name is Dominic Fischer, and I work at Bloomberg, where I do C++ for the last 5 years in platform security. We do a lot of IO-heavy based workloads, which is why I'm particularly interested in coroutines. And also, I made this series, Coroutines for Dummies, which is a 4/5-part series, depending on how much time I have, basically explaining coroutines to my colleagues and friends at Bloomberg, basically. And I was told it was a good idea to kind of present this outside of Bloomberg as well, because it was well received. So here I am. So the goal for the agenda for today, first I'm going to discuss what a coroutine is. So this will be outside of C++ and also within C++, the concept of a coroutine. And then we're going to look at the keywords that were introduced in C++20 for doing coroutines. We're going to look at the famous coroutine promise type you might have heard of if you've done any research. If you don't know, it's fine. I expect all of you to be dummies anyway for this presentation. This isn't going to be a comprehensive deep dive. I'm not going to comb through the spec, telling you every nook and cranny of every possible thing that you can do with coroutines. My goal for today in this 90-minute session is just to show you the minimum you need to basically get started and empower you with enough information for you to then go read the CPP reference, for example, yourself, and have a clue of what you're actually looking at to get started. Also, note that because I'm going in such a bare minimum approach, I'm kind of showing you how to juggle knives without telling you that you're holding knives. So don't just go write some coroutine code and ship it to production immediately. Go read some docs first, learn the semantics, the safety rules, lifetimes, all of that. Here, I'm just trying to implant ideas into your mind. I'm not trying to necessarily teach you precisely how to do things. Right, also because I'm simplifying things quite a bit, sometimes I won't tell you the full story. I might lie to you a little bit, or there'll be some exceptions to what I say, in which case I'll be using that emoji, which is an emoji with a long nose. If you know Pinocchio, when he lies, his nose gets longer. That's why I picked that emoji. So when you see that emoji on a slide, it means that there's more to the story, or I'm not telling you the whole truth, or something like that. So just a little grain of salt, asterisk. That's just a fun version of an asterisk, I suppose. I will have breaks during the presentation to take questions. So if you're shy about interrupting me, you will have your moment of silence to raise your hand and I'll take your question. But if you feel like asking me something in the middle of it, feel free. I hear this is how we do it at C++ now anyway. So anyways, let's get started. So first off, what is a coroutine? A coroutine is a function that can suspend its execution and be resumed later. What that looks like is, here's your irregular function. So all it does just does 3 things. It prints out hello, prints out hi, prints out how are you, and then returns. Very simple, no smokes and mirrors. It does exactly what you think it does. You call it, it runs to completion, and it returns to you. Now the coroutine, this is more like pseudocode. You can insert these suspension points, for example, between statements. So you can say, I want to print out hello, suspend, so the coroutine stops. You can then go do something else, come back, resume the coroutine, then it'll do hi, it'll suspend again, you can go to something else if you like, come back, and then resume the coroutine again, it'll do how are you, and then the coroutine is complete, and the coroutine is run to completion. So conceptually, this is kind of what it looks like. More concretely, if you were to write this in actual C++ and not just pseudocode, it would look something like this. So you will have this state machine, which is the coroutine, and it just has a little integer in it to track what stage of execution it's in. So like for the initial stage, which is 0, when you resume it, it'll print out hello. Stage 1, it'll print out hi. Stage 2, it'll print out how are you, and then there's no more stages after that, so there's a little assert to catch that. And then at the end of the resume, it just increments to move to the next stage. And we have this do the coroutine function, which just returns a brand new coroutine object. And then in your main, you can get this coroutine and call resume 3 times. So you can imagine in between those calls to .resume, you can go do something else. That's kind of how the suspension works. So whilst there's a resume call active, the coroutine is running, and in between resume calls, the coroutine is suspended, right? Now, this is, as you can imagine, a rather tedious thing to have to write, which is why we have a nice new fancy feature in C++20 to have coroutines, where the compiler can basically look at, you write something that looks like this, and then the compiler can then write this for you. You don't have to go through all this bit of boilerplates. But moving on. So what about a C++20 coroutine? What does it actually look like? What are the new features? So in C++20, a function is a coroutine when it uses one of these three keywords: co-await, co-yield, and co-return. If you see any of these keywords in the function body, it is a coroutine. If you do not see any of these keywords, it is not a coroutine. Full stop, right? The implication of this means that if you look at the signature of a function alone without seeing the body, you actually cannot tell that the function is a coroutine. You just can't tell without looking at implementation, right? You can look at the return value and infer and say, oh, this looks like an asynchronous type, so this is probably a coroutine, maybe. But you don't know for sure. You can just take an educated guess, and things can always change. So that's an important thing to note about coroutines. And a little extra note, so you're not allowed to use the regular return keyword you know and love. You have to use co-return. They basically do the same thing. Right, just to explain each keyword really briefly. So co-await, if you've used async await in other languages like JavaScript, C#, Kotlin, that does the same thing as those, the await in those, just basically a way to wait for something that will complete later. If you've worked with generators, co-yield works like yield does in Kotlin, C#, Rust, etc. Suspends execution while returning a value, and co-return is just a return, like I said. But details. I will explain in detail in later slides. But most importantly, let's start with co-await. In my opinion, this is the most important keyword when working with coroutines. As once you understand how co-await works, I think you're set. Everything else is just minutia built on top of how co-await works. So this is the most important part of the presentation. For the next 20 minutes, I want you to lock in, focus on this bit, and then the rest will be details. So what co-await looks like in use, there's these two forms. So co-await takes an expression on the right-hand side, and then optionally can produce a value, which is stored on the left. The first form returns a value. You can store it in a variable, or you can choose to discard it in the second form. Or if the expression, when you co-await it, gives you like void, for example, then there's no value to store in. Both of the two invocations you can use. Now, the expression you give to co-await on the right must resolve to an awaitable type. Now, what is this awaitable type? On a high level, an awaitable is simply something you can wait for, right? So, for example, if you imagine sending out an HTTP request and you're waiting for the response, this is something you can wait for. It's an awaitable type. So, an HTTP response is an awaitable thing, or like a SQL query, something you can wait for, or like a timer, right? These are things that, there's nothing you can do from your process to basically control when these things come back to you, because that's how I/O works. You have no control over when the HTTP server is going to respond, when the timer is going to fire, because nobody can control time so far as of filming. So formally, what an awaitable type looks like in C++ is a struct or class, I think even union as well, that has these three methods. So await ready, await suspend, await resume. As long as you have these three methods, you're allowed to co-await this type. Of course, the methods have to have the correct signature. There's a few valid signatures you can use, and they all have different use cases. I'm not going to talk about all of them because they require a lot of context to understand. But this is the simplest form. This is what we'll be focusing on today. So to explain each one quickly, so await ready is the first thing that's called when you co-await. It's a compiler's way of checking, do you have the result of your operation right now? So most times this will be false. For example, if this is like an HTTP request, you probably haven't sent the request out yet, or the response hasn't come back yet, in which case you're not ready, right? But if, for example, you have, say, a cache in front of this HTTP, like library or something, let's say you want to retrieve like a name behind an ID, but you already have this ID in the cache. Inside your implementation of ready, you can see, is this already in the cache? Then we're ready. We have the response. We don't need to send a request out. We're ready right now. That's kind of the idea. It's just a very quick optimization to just check if you have the result right now, so we don't need to suspend the coroutine. Then we have await suspend. This is called after the compiler suspends the coroutine. So once the awaitable declares, I'm not ready, sorry, there's work going on in the background, the compiler says, all right, cool. I will pack up all the local state in the coroutine and put it in this coroutine handle thing, which I shall explain later. and then call await suspend. So in the awaitable, it's going to know in the await suspend call that the coroutine will be suspended, and at which point it is its responsibility to resume the coroutine later when it's done, right? When the HTTP response comes back, it shall resume the coroutine, that sort of thing. And then await resume, very simple, it just returns the results of the operation, right? It returns the HTTP response or the SQL query results, that sort of thing. And at the bottom is what the invocation would look like if you're co-awaiting this type. So you have my result equals co-await my awaitable. So you can, if you note that the return type of await resume is the same as what is returned from co-await. So that's literally like just a direct, the value returned from await resume is just passed through what is returned by co-await. That's an important thing to note. Right, so more about the coroutine handle that I glossed over. Basically, if I was to give you like a formal definition, it's just a pointer to the coroutine. But as dummies, that more or less doesn't mean anything to you. Pointer to the coroutine, what does that really mean? So I'm going to give you a more layman explanation for what this coroutine handle thing is by piggybacking off of something you've hopefully already worked with, which is callbacks. Yes, if you've dealt with asynchronous code at some point in your career, you've probably seen callback APIs and worked with them. And if you've worked with them enough, you probably hate them as much as I do, because I'm sure you've heard of callback hell, or if you've ever tried to write a for loop with callbacks or recursion, or even just if statements, you will know why these are really annoying to work with. But anyway, it's something that most people already know how to work with. Right, so for this example, let's imagine we have a key value store, right? Something like, let's say Redis, or maybe even like Postgres, the table has key value. But the point is, to access this key value store, we have an asynchronous API, so load from store, which takes a key and a callback, and in this callback is where you receive the value, right? Now, if you want to use this load from store function, in this doing thing function here, we would call load from store with a key. So we've declared a key, which is Dominic, that's my name, and then we pass in a callback. So this load callback, all it does is print out the key and value, right? I want you to note one thing, that in the API, the load from store API, the callback only ever provides you the value. It doesn't give you a copy of the key, right? And because of that, we have to use std bind to basically take a copy of the key to make it available later in the callback so we can print out both the key and the value, right? Cool. I'm going to give you a few moments to just stare at that code before I move on. Also, this is one of those breaks for questions if anybody has any.
So all of these functions are like normal functions where one of these function is, the first one you are just passing a function as an argument?
Yeah, these are all regular functions, no coroutines here whatsoever.
Yeah, so you mentioned coroutine handle. So is there anything related to coroutine here?
Not yet. So conceptually, yes, but concretely, no.
All right, makes sense. Thanks.
Yeah. Cool. So, right. So regarding the copying of the key to make it available in the callback, I want you to note that, so normally, if say we didn't actually bind the key to the callback, after after load from store returns, right, it's going to set up, like in this implementation, it's going to set up a callback somewhere to run later. But while that's happening, doing thing is going to exit, and then the key is going to be destroyed. That state is going to be gone. However, we need it later. Right, so basically, conceptually, what we're doing here is we need to preserve the state that we have, which is not a lot of state, just a single string. But we need to save this string so that later on, when we continue the work we're doing in the load callback, it's available, and then we can print it, right? Conceptually speaking, when the compiler does suspension, right, this saving of the coroutine state is the same thing we're doing here when we take a copy of the key and bind it to the callback, right? We're kind of doing the same thing the compiler will be doing when it suspends the coroutine, right? And now you can then picture this std bind call, the return value of it, as basically the same thing as what a coroutine handle is. That's what the compiler is kind of doing. So the coroutine handle is basically like a glorified callback, just some way to make the coroutine continue. So yeah, that's the similarity here. So right now there's no coroutine stuff on this slide. It's just conceptually I'm pointing out that the std bind, what we're doing there, at least the return value is the same thing as the coroutine handle, which is a glorified callback. Right, so, does anybody have any questions about what I think I said now? No. Cool, so, let's look at what the compiler kind of does with the co-await call. Now, I just want to be clear that I'm not speaking about any specific compiler. I'm not saying like GCC or Clang or anything, any of them do this. I'm more discussing the compiler contract, like what it ought to be doing for you. What it's actually doing, they all have their fun quirks at the moment regarding some of these things, so I'm not going to go into too much detail as to what they do, just a high level, what you should be expecting them to do, right? So at the very top, we have the comment, my result equals co-await awaitable. So if you write that, all the code below is what the compiler should be more or less generating. So you have your awaitable, which is stored in a local variable. I don't want to say stack variable because that's a problematic term in this context, but it's a local variable. And then the first thing we do is check call await ready. Are you ready now? Do you have your result? Right? If the result is ready, we skip the if statement, we skip all the interesting stuff and just fall through to await resume and get the results and then move on. No suspension happens, we just get the results of the operation immediately, right? Now if the awaitable is not ready, which is what happens most of the time, more interesting stuff happens. The compiler goes, okay, you're not ready, we need to suspend everything. Then we have that little comment, compiler suspends the coroutine. You can imagine that std bind kind of happening in that little comment there to save all the local state that we might need later. Right? Then we get the coroutine handle, which is just a glorified callback. And then awaitable.await suspend is called. You tell the awaitable, the coroutine is suspended, here's a callback to call. Call this when your operation is complete, right? Call this when the timer runs out. Call this when the HTTP response comes back, right? That's the idea. After that, the coroutine is suspended, it stops running. You can imagine that as kind of like almost hitting a breakpoint in the debugger. It just halts there. And at which point, some other code will be executing, the control returns to the caller to run something else, but the coroutine stays there. Now eventually, hopefully, the awaitable is going to resume the coroutine. So it does that by calling handle.resume. You can imagine that as kind of like invoking the callback. And then the code just continues from after await suspend, just falls through, and then await resume is called to get the results of the thing we're waiting for, and then we move on. And that's how that works. I'm going to pause for a little bit just to let you read that again.
So like we never go back to the if condition?
No, it's checked once. So if we're ready, we just skip all of that, and if we're not, we suspend and then eventually resume and fall through. We don't go back. Yeah. Cool. So let's write an awaitable type, okay? So we're going to bring back our load from store function from earlier. Same thing, takes a key, gives you the value via a callback. And we're going to wrap that in a struct, which is going to be an awaitable type. So this struct just has two members, just the key that we're trying to load, and then the result to store it in. Sorry, what's the question?
Yeah, so I see all of your functions have string and everything in pass by value.
Yes.
Is it intentional, or like does it have any implication?
It's just to make the code smaller. So I could have a const ref and like to say by reference. It's allowed, yeah. I just chose to make the code shorter. Yeah. Right, so we have this awaitable struct which has the key and a place to store the result, so an optional string, and then a boring constructor which just takes the key, and then await ready returns false because we haven't called the load from store API, so we're not ready yet. We want the coroutine to suspend. And then in await suspend, once this is called, we know the compiler has suspended the coroutine, and at which point now is as good as any time as ever to actually start doing the work we need to do. So we call load from store, pass in the key we want to load, and then we pass through a callback. We capture the awaitable handle, and then we get the value. And the first thing we do inside the callback is store the value inside the optional result, and then resume the coroutine, right? And then inside await resume, what we do there is just return the result to the caller. There's an assert there, this is a sanity check. I'll explain why that's needed in a bit, but that's what that's for, it's a little sanity check. And then
doesn't value check as opposed to the star?
Sorry?
Doesn't the optional value have a check? itself?
Oh yeah, it does. I think it does. I don't. I'm trying to remember if it's always on.
If
But
you
then it
do-
matters.
If you use the star, it's not checked by default unless you turn on
Okay.
extra check.
I don't remember specific. I know like in some cases there is a specific check, but the me putting the assert there was more to illustrate a thing I'm going to explain in a bit. But yeah, you're right. We don't strictly need to check that, but yeah, yeah. But if we're going to prefer to use this awaitable down in do the thing, we create the key, the same, which is my name, and then we just do awaitable load, pass the key through, and we get the value back, and then we print out the key and then the value. Which is the same thing we're doing in the load callback function earlier. And I wanted to note how we don't have to do any work to kind of like capture the key to use it later. The compiler kind of does the work of preserving the local states for later use. Now to address the assertion. So if you look at the callback in await suspend, where we call load from store, you note that the result is stored before the handle is resumed. If those two are swapped, so we resume the coroutine before storing the result, that assertion in await resume will fire. No if, no buts, no maybes. This is not a case of like, this might be a race condition where you call handle.resume and then some event loop somewhere is going to eventually call the coroutine, at which point maybe you've stored the result by that. No. Immediately when you call handle.resume, inside like the stack frame of that call, the coroutine is going to continue. So the call to await resume is happening inside the handle.resume call, right? So that's why I put that assertion there to kind of highlight the fact that like, if you swap those two, you kind of have that programmer error where you haven't stored the result yet, even though you've asked the coroutine to continue. Yeah, so, right. Also another thing I want you to note is that thanks to our use of co-await, we no longer have to directly work with callbacks. Yes, there is a callback inside this big old awaitable struct, which is a lot of boilerplate. I just want to say, if you're using coroutines in actual production, you're not going to be writing these gigantic awaitables. You'll be using a coroutine library that like hides all of this from you. Any half-decent coroutine library will have this inside it for you, and you will never have to write this. You only have to write the code that's at the bottom, do the thing. You would never have to write an actual awaitable yourself. Well, I won't say never, but very rarely would you have to write it. I guess if you're working with an API the library hadn't thought of, then you'll need an adapter. But the boilerplate here is just to highlight how co-await works. But I don't want this to kind of put you off like coroutines, like, oh, this was complicated. No, it's just explaining how it works. A library would hide all this away. But yes, just in case you haven't worked with async await before and might not be able to appreciate the callbackiness going away, I want you to first imagine, let's say inside do the thing, here we're just loading one key to get one value, but if we wanted to load n keys, let's say we had a vector of keys, like 10 keys, and we wanted to load all of them, one by one sequentially, because you don't want to overwhelm the key value store. Those are the rules. I don't make the rules up. That's just how the API works. Here, you could just do a for loop, a for each loop. For each item in a vector, call co-await awaitable load, and then store that in another vector. Nice and simple, like you do with your asynchronous blocking code. However, if you were to work with that callback API directly and do that, you're going to have to figure out how to pass this vector around, maybe with a span, and then ask it to load the next one after the other one is done, store it in the vector, have a final callback to. It's just no fun to do all of that. Just here, we have a nice and simple for loop. With that, you can have your if statement, you can do recursion, nice and simple. Yeah, I'll just pause for a little bit for any questions also. Stare at the code. Yep.
Don't call handle or resume.
Good question. So if you never call handle or resume, you basically, so in the do the thing function, after it does co-await awaitable load, it just would never continue. Just have a deadlock, yeah. All right. So we just wrote our own awaitable type, but actually the standard library provides us with some minimal ones that are useful in a lot of situations. So we have suspend never, and we have suspend always. So suspend never is very simple. It just never suspends, immediately resumes. So when it's await ready, always returns true because it's always ready to go. Await suspend is never called because await suspend is never called because await ready is always true. So we could put like an std terminate instead suspend, await suspend, and then that just never be called. And then await resume does nothing. So you can pretty much think of a co-await suspend never as a no-op. The compiler could just remove that and then like it would make no difference. Of course, there's a bit of an asterisk there, There's a lot of customization points to coroutines. You can make it such that it's not a no-op in your coroutine type, but by default, if you don't do anything special, you can consider it a no-op. Suspend always suspends and never resumes. So it's never ready. It's await suspend, just discards the handle, doesn't do anything with it, and await resume does nothing. So after hearing that explanation, if you're thinking, hold on, if you co-await suspend always, doesn't that mean that your coroutine just gets stuck forever? Yes. You are. If you're thinking that, you're on the right track. However, asterisk, of course, there are other ways to resume a coroutine besides doing it from an awaitable. But that's an advanced topic. Dummies don't need to know about that just yet. But yeah, these are the two simple awaitables that are very handy to use when you're writing your own coroutine type. The standard library, to my knowledge, doesn't provide any other awaitable types. It's not until 26, which has some fun stuff. But yeah. Anyway, next up, the coroutine return object. So far, the coroutines I've shown you, which is, I think, just one, the return type was void. That's actually, the compiler would not be too happy with that. The return type of your coroutine has to follow some rules. It needs to satisfy some conditions to work correctly. So looking at this code example where we have an actual proper return type. So here we have this my coroutine return type of this do something coroutine function. So we have those just some co-await, co-yield, whatever, just to tell the compiler this is a thing I want you to turn into a state machine. And then at the bottom we have my coroutine type, and all this return type needs to do is to have a member called promise type. Asterisk, there's other ways to do that, but for dummies, this is what you care about. It's just to have a promise type inside it. And then the promise type itself needs to have some member functions inside it to conform to what the compiler wants. Now, on a high level, what this promise type is, this is where you specify customization points to define the semantics of your coroutine, right? This is where you decide, is your coroutine going to be an eager one or going to be a lazy one, right? Or like, what kind of values are you allowed to co-yield, or are you allowed to co-yield at all? Like, or what are you allowed to co-await? What are you allowed to co-return? This is where you define all the rules and regulations of your coroutine body. Right, I'm going to go through the members. So the first one is getReturnObject. So getReturnObject you can think of as just like a factory function, almost like a constructor. That's the signature, so it simply returns the return object, and then a constructed implementation returns it. And then the code below just shows the ideal, this is how the compiler is going to call your functions. The first thing it does is going to allocate a new promise type. And yes, it uses a new keyword, there's allocations here. Unfortunately, there are optimizations to make them go away, but yeah, by default, there are allocations. So make a new promise type, and then it'll call getReturnObject to actually get the instance of the return object. And then it'll return it as soon as possible. This is typically after the very first suspension point. This very real, first real suspension point. Yeah. And next up, we have initial suspend. So initial suspend just returns an awaitable type of your choosing. And then the compiler just calls at the very start of the coroutine. So this is inserted just before the body of the coroutine you write, and it just does co-awaits initial suspend. If by default you don't want to actually use initial suspend to do anything interesting, you can just have it return suspend never, right? And if you remember from earlier, if you co-await suspend never, it's a no-op. So basically that call just disappears. Typically, if you want to, this is where you would decide whether or not your coroutine is eager or lazy. So an eager coroutine would return suspend never, because this just be ignored and then it'll just immediately execute the body. A lazy coroutine would return suspend always, so it'll immediately suspend, and then at which point it is up to you to then figure out, when you want to start the coroutine as opposed to doing it immediately when you call the function. That's what that is used for. And next up we have final suspend. This is inserted at the very end of the body of your coroutine. While I say it's at the very end, this is more like after a return or throw kind of thing. So even if your body throws an exception, final suspend is still called. This is typically used as like cleanup. It has the same signature as initial suspend. So it returns an awaitable type of your choosing. If you don't wish to use it, you can simply return suspend never, and it's a no op. You don't have to worry about it. Yeah. Next up, we have return void and return value. These are much simpler functions. Basically, what the compiler does with them is that when you do a co-return inside the body of your coroutine, it's replaced with a call to either return value or return void. So if you do co-return with some value, then return value is called. If you do co-return without anything, return void is called. In your coroutine, in your promise type, you can't have both defined. You have to pick one or the other, which there isn't really, I don't know of a use case to really use both. Except when you're kind of trying to do some template stuff, it can kind of get in your way, but there are workarounds for that. So don't worry about that. Just remember that you can't have both in your coroutine body. And also, in return value, the type of the parameter of return value determines what you're allowed to co-return. So if you have a single return value defined in promise type, which takes an integer, then you're only allowed to co-return integers, right? If you take a string, you can co-return strings. Or if you put a concept there that says you can take like XYZ type, then you can co-return those. But that's how you decide what you're allowed to return, right? And last, and arguably the least, unhandled exception. So how this works, basically you can imagine the entirety of your coroutine body is stuck into a try-catch. And then if any exception is thrown, promise unhandled exception is called. This is where you can actually gracefully This is where you can capture an exception thrown by the body of your coroutine and propagate it to the right place. So if you subscribe to structured concurrency, this is where you propagate like the exceptions or the parent's coroutine sort of thing. Yeah, that's what that's for. And also remember that final suspend is called after an exception is thrown, regardless. Yeah. So putting all of that together, we have our MVP promise type, just minimum viable, with all the customization points. So get return objects, initial suspend, final suspend, all the good stuff. And all of this together, this is how you can expect the compiler to kind of invoke your promise type functions in your coroutine body. Yeah, I'll give you a few moments to look at that or take any questions. All right. Well, I take it now you're all experts on how co-it works and the promise type. So next up, I have some demos. Yeah, some code to compile. And I'll have some questions for you, the audience, if you don't have any questions for me. 1 second, let me switch this over. Hopefully this can be done gracefully. Hold on. All right, cool. I can see what you're seeing now. Right, so for the first demo, this is very basic. So we have that same my coroutine MVP type from earlier, which just has a promise type, does very basic stuff, suspend never, nothing too interesting there, we're not focusing on that. But in here, we have a do something function, which is a coroutine that prints out hello from coroutine. And then we call this from main. So my coroutine got an object called that. And then we can see the output on the right, hello from coroutine. And that's there. Right, so some questions for the audience. So first question is, see this on line 9, this suspend never being returned from initial suspend. How do you think the output is going to change, if it will change, if I change this to suspend always instead of suspend never?
Can you increase the font a little bit?
Oh yeah, sure. That all right? Okay. I'll give you a few moments to think about that, then I'll ask for a show of hands. Okay, show of hands, who thinks the output will not change? Okay, show of hands, who thinks the output will change? Okay, cool. Who's brave enough to tell me why, like, what the change is? Go for it.
So I don't, it suspends ever, and I don't see anything resuming it, so I would not expect it to print.
So that printout wouldn't show?
I don't see anything that would make it. I'd expect it not to show.
Okay, cool. Yeah, that's correct. Yes, so nothing will show up. So I just let me just give you a little just prove it. So I'm not saying it. Yes. So nothing comes out. So at the very start here, if I remember from earlier, the compiler will insert a core with initial suspend at the very start of the coroutine body, and then when you call it suspend always, the coroutine just kind of deadlocks there, and there's nothing to explicitly resume the coroutine, like you said. So yes, nothing comes out. And here's another fun one. What happens if I comment out line 19, this co-return? How do you think the output would change? I'll give you a moment to think about it. All right, show of hands, who thinks the output will not change? Okay, who thinks the output will change?
You're just going to comment it out?
Yeah, if I just comment it out, yeah.
It won't compile?
Yeah, correct, yes. It won't compile, yeah. Because if I take this out, then it will complain that I'm not returning a value. Yeah, that's so simple. It's a little trick question. Yeah. And one last question before I move on. So here,
did you explain why it doesn't
Because it's
compile?
not a coroutine.
Oh yeah, because we don't return a value. So like if you
It's not a coroutine if you comment that out.
there's also that, yeah.
This is important.
Sorry?
This is important comment.
Yeah, that's the point. Yeah,
It's not a
that is.
coroutine.
It's not. Yeah, because the first time when I thought of this question, I was trying to go for it. This is not a coroutine, so the printout will happen because the initial suspend is not going to work. But then I commented it out, and then the compiler error happened. I was like, oh, okay. But yes, compiler error aside, once you remove coroutine, it's a spoiler for the next question now, but it doesn't matter. Once you remove the co-return, this is no longer a coroutine, which means none of the promise type stuff matters, and the printout would show up, assuming we returned like something. But anyway, this is a really easy question. But so we have hold on, a question.
So when you converted it to suspend always, right?
Yes.
So if you did that, this object will be returned.
Yeah.
And then I would need to call something on it to actually have it.
Yes.
Is that
Correct.
okay?
Yeah.
So I'm operating on like it's a captured state.
Yes. Correct. Yeah. So yeah, that's exactly right. With this returning suspend always, you would need some other mechanism. So you would expect an API like this to say you'd have like a sort of maybe a start kind of thing, and then the implementation of start would resume the coroutine for you.
Is there a specific pattern for suspend always where that is appropriate?
Okay, this is more of an opinion answer as a fact, but I would say most coroutine libraries would be giving you lazy coroutine, so most of them would be actually doing suspend always, but the idea there would be you wouldn't have to explicitly sort of start the coroutine. It would be if you co-await the coroutine, then the scheduler, yeah. So that would automatically kind of under the hood start it for you. So you can first create a coroutine object and then later co-wait it and the co-waiting will start it. Or some will have like a sort of way to, rather than co-wait, you can blockingly wait for it. Then that'll also start it for you. So I wouldn't expect any coroutine library to have an explicit like start call on it, but that's my opinion, of course. I mean, yeah, everybody's free to write their own library for what works for them, use cases. Cool. With any other questions before I ask the next question? Cool. So, nice low-hanging fruit question. So we have this do something else function that calls do something here, and it just returns a coroutine. So take a moment to think about it, but do something else. Is it a coroutine or is it not a coroutine? Show of hands, is it not a coroutine? Show of hands, is it a coroutine? Okay, if you said it is not a coroutine, you're correct. Do something else is not a coroutine. But do something is a coroutine. Of the people who said this is not a coroutine, who's brave enough to tell me why?
Well, so in practical terms, for the caller, it effectively behaves like a coroutine because the return value is returned from a coroutine.
Yeah.
But it is not itself a coroutine.
Correct. Yeah. That's precisely right. Yeah, gold star. So I couldn't have said it better myself. Yeah. So as far as the caller is concerned, it kind of feels like a coroutine, but this itself isn't a coroutine because it doesn't use any of the three magical keywords: no co-wait, no co-return, and no co-yield inside. So this is not a coroutine. It just more like a proxy function to call a different one. So this is something to watch out for. Sometimes people make this mistake thinking it's a coroutine when it's not. But yeah, hopefully you don't run into that too often. Anyway, yeah, that's it for that demo. Let's move on to the next one. This one is a bit more interesting. Now we have threads. So we have the same my coroutine from the previous demo. Nothing too interesting here. Don't focus on it. But we have a waitable type. It's called my sleep. High level, what this my sleep is just a way to delay for a fixed amount of time. That's all it is. And the constructor takes the amount of time to wait for. We're not ready. And then inside wait suspend, we create a thread. I know it's wasteful, just ignore it. We make a thread, we sleep for the duration, and then we resume the coroutine. Afterwards, we then detach the thread. Sadly, there's no nice and obvious place to join this in here. A proper coroutine library wouldn't have this problem. It's just slideware. That's just what we have to do. That's my sleeper waitable. And then here we use it in doing something. So first we do a print out, hello from coroutine, print out the thread ID, sleep, print, print. Nothing too interesting. And then in main, we just have a print out, hello from main. We call do something. And we have, this is just a sleep just to make sure everything finishes before we exit. There are more proper ways to do this, but I don't want to make the code any more complicated, so don't focus on it. Here's the output. Okay, this is going to be a struggle. That's good enough. Okay, you can see that. Right, so the first thing I'm going to ask you, the audience, so if you see these last three calls to, the last three log lines, where I've printed out the thread IDs, they're different. Like this and this are the same. That's a bit of a coincidence. Don't focus on that. These two are different. Is anybody brave enough to tell me why these thread IDs are different? There's no trick. If you're thinking of something, it's probably that. But, yep.
So it's a async process, right? So what it does, the scheduler, just because you call coroutine, scheduler does not have to be putting it in multiple threads async to make it work. If it thinks that your process has a lag or it can wait or sleep or something, and if it benefits by sequentializing it, it will sequentialize it over parallelizing it. So that's why you may end up seeing same thread doing two different parts of coroutine.
Okay, if I'm understanding what you're saying properly, you're saying that there's a scheduler runtime somewhere, and that could decide to then run the coroutine on multiple threads or a single thread depending on what it does. So that would be an explanation for why we're seeing the thread IDs.
Yes, so I think the first and third one, Circumstantially, it was more beneficial for both of them running on the same thread than creating another thread and running parallel.
Okay. I understand why you said that, and it's a little unfortunate that the first and second thread IDs are the same because they should.
There's actually a reason they're the same.
Sorry?
There's a reason they're the same.
Okay.
It's actually starting new threads, but the first time you enter, you start a new thread. In that thread, you launch a new thread.
Yeah.
But then the first one is detached and finish.
Yeah.
So now your first thread ID is now free and can be reused.
Yeah, it's been reused. When I run this, so we have. Am I allowed to say this here? So I have a different instance of Goldbolt running. That's not the official one, and that actually has unique threads. I think it's just a different operating system.
Yeah, this is going to be very system dependent.
Yeah, of course. Yeah, it's different.
The middle one is always going to be different, though.
Yes, because of the you're right. Yeah, precisely that. Oh, yeah, sorry. But getting back to what you're saying, you kind of had the right reasoning, as in to suspect that base and thread is being the same, the first and second. But that's a bit of a distraction. My apologies for that. I could have gone out of my way to make them more unique. But I want to clarify that by default, when you're doing coroutines, the standard doesn't provide you with any kind of scheduler, runtime, event loop. All we have is just plain state machines, right? So the only threads that are running in this demo here is the main thread, which is what's started by the runtime, and the threads I'm creating here. So there's no sort of scheduler behind the scenes. It's just what we're seeing, at least. But yeah, I'll take that as a half answer for the question. The thread IDs are different because I'm making fresh threads here and resuming the coroutines inside the new threads I'm making. The next question I'll ask is, so if you notice in the second log line and the third log line, the thread IDs are different. Now, both of these are coming from the coroutine. Oh, no, I'm not asking that right, sorry. No, the first and second log lines have the exact same thread ID, right? Rather than different ones compared to the rest. Is anybody brave enough to tell me why the main thread ID is the same as the thread ID being printed out from the coroutine?
I mean,
Go for it.
you only start a new thread when you call sleep.
Yes.
So until you call sleep, you're still in the main thread.
Correct. Yes. Gold star. Yeah. I should have gold stars here to hand out. I should have make this more fun. But yes, that's correct. So when I call do something, the first part of the coroutine is going to be running directly in the main thread, and only after the first call to my sleep is a new thread actually created. At which point the coroutine will be resumed inside this new thread that is made. And so on and so forth. Cool, okay. So here's an easy question, no tricks. This is a low-hanging fruit. So here on line 35, we have an initial suspend, returning and suspend never. How is the output going to change if I change suspend never to suspend always? I guess I'll give you a moment to think about it, then I'll ask for a show of hands in a little bit. So show of hands, who thinks the output will not change? Okay, show of hands, who thinks the output will change? Okay, cool. Who's brave enough to tell me why it will change and how it will, yeah?
I got here pretty late, so I might be totally wrong about the answer, but when you suspend always, it never sets off the task. So the first sprint, the hello from coroutine would run, but then after that, none of the other ones would run.
That's very close. The right reasoning, but with the exception that the first hello from coroutine won't show up either. So inside doing something here, the initial suspend call is inserted in here. Mm-hmm. So this is where it would get stuck at this point, and then nothing else would run. But you had the right thinking there. I assume everybody was thinking something similar because this is the same as the previous demo anyway. All right. Question.
This is more of a, implementation question. Is it guaranteed to be from the prologue that gets set up, is it like the first thing after that? Is that what this sort of that this is provided? Where the coroutine, if you scroll up,
Yeah.
where actually scroll a little more.
Yeah.
Where that initial suspend,
Oh
is
yes.
that literally the very first thing that is done after the prologue that function is set up?
So after the promise type is constructed and we get the
But that's what I'm saying. The promise type
okay.
is created, that is the first thing that is done. There is
Yeah.
nothing that happens.
yeah, nothing happens before that. Yeah. Yeah. The order between initial suspend and get return object, don't quote me on this. I don't know if it's defined for one to happen before the other. I remember seeing a Stack Overflow post somewhere saying that one compiler does it one way, another one does it another.
Is it
I don't know.
arguing spelling, any of those kind of things? Like, I'm curious where that actually would happen.
Yeah, that's a good. I couldn't answer.
But it's before any user code. Before
Yes.
any user written code.
Yes, correct. Yeah. Right. Cool. So some more fun stuff. Here's a fun another question. I can't say there's no tricks here, but if I change final suspend to do suspend always instead of suspend never, how do we think? First of all, how do we think the output is going to change if it does change? So I'll give you a few moments to think about that. So final suspend, if I change the return type to suspend always instead of suspend never, the output, how is it going to change? So a show of hands, who thinks the output will change? Okay, show of hands, who thinks the output will not change? Okay. A show of hands, who doesn't know what's going to happen? That's fine.
What's the code is below?
Sorry?
What is the code below?
Oh, below, okay. Like this?
Oh, okay. Yeah, that will change.
Okay. Right. Okay, so if you thought the output will not change, you'd be correct. The output will not change. Just to make sure I'm not. Check. So 5 log lines, loading. My output is slow today. Yeah, same output. Even here, the thread IDs are still matching. Okay. Yeah. So the reason why, oh no, wait, no, why am I spoiling this? So for the people who said the output will not change, is anybody brave enough to tell me why? Yep.
So it's running forward normally until it gets to the end, until it gets to the very end of the coroutine, at which point it's running in a detached thread. So main will exit normally, and this thread will return and just finish also.
Yeah, I'll give you 9 out of 10 for that. But the point, the bit to highlight is that final suspend is called at the very end of the coroutine body. So regardless of what your final suspend is doing, the whole body is still going to run first.
Right, it's just a question of whether it causes anything else odd to happen.
Yeah.
And I think it doesn't.
Yeah. I was going to ask that after this one, but just the output alone is going to be the same because, yeah. Now, technically speaking, I haven't actually said this in my slides, so you're not expected to know the answer for this, but just a little bonus question, for people who already know coroutines. What, besides the output changing, what behavior do you expect to change in the program from me just going to suspend always? Is anybody brave enough to? Yeah, Dietmar.
The coroutine frame will be leaked.
Yes, it'll be leaked.
And you
Unfortunately.
can prove that, by the way.
Sorry?
You can prove that as well, by the way.
Oh, as in if I override new and delete, I can show the delete is
No,
not called, or?
Well, you could just put into your coroutine something which prints something upon destruction.
Oh yeah, that will also work. Yeah. I'm thinking, am I brave enough to type this live? Wait, how much time do I have left? Let's see.
At least
Oh, I
that's-
see. I'll come back to that. But yeah, that's correct. The coroutine will be leaked. This is technically out of scope of this slide, but I'll just quickly explain that since I asked the question. So when you do suspend never, return that from a final suspend, you basically get like automatic cleanup. So the moment your coroutine kind of falls to the end here and you go to co-return, it's automatically, the frame is automatically destroyed. However, if you do suspend always, the coroutine kind of stops there and it stays alive. This allows you to... explaining this without code snippets might be hard. But it is sometimes useful to kind of have the coroutine frame still be alive, even after it returns. Explaining why without some code snippets will be difficult. But just know that those are the two semantics of final suspend, I guess. More will be explained in part 3 of this series. Cool, all right. So next question I'll ask is, so let's say we take this, copy that, and put it here. Right, so all this does here is print out. So we're gonna print out hello again from main and print out the thread ID, right? And this happens after we call do something. So my question to you is, if I uncomment that line, first of all, is it gonna show up in the output? And if it does show up, where in the output is it gonna show up, right? Okay, I'm gonna give you a moment to think about it, and I'll ask for a show of hands. If you want me to scroll or anything, you can ask, that's fine. Right, okay, ooh, 20%. Oh, that should be fine. Oh, I didn't plug it in. Oh, it's okay. Right, so quick show of hands before my battery dies. Who thinks the output will not change? Okay, that's good. Who thinks the output will change? Okay, I kind of gave you hints there when I said it. Okay, right. Right, so I guess we all think that this log line is going to show up, I guess. Or maybe more log lines will disappear. I guess I don't put words in your mouth. But we'll just assume the log line will show up.
Did you do some thread detached somewhere?
Sorry?
You did some thread detached somewhere, right?
Yes, there's a thread detach in my sleep. So here. So I spawned the thread and immediately detach.
Okay, it's in the my sleep.
Yeah. Yeah. Okay. Right. So if I assume this log line is going to show up somewhere in this output, is anybody brave enough to tell me where in the output is going to show up? Oh, nice. Yeah.
It'll be after hello from Coroutines.
Yes! 10 out of 10. Go star.
At
Right
least
after that.
assuming you have normal timings, because
Yes.
Oh, yeah, sure.
it's a race.
There's no guarantee that that happens.
Because there's have a detached, you're waiting in a detached
Right.
thread.
If you make your time small enough.
The first code.
Yeah, that's...
That's still in the main thread, so it would have to happen.
The first code.
Yes, we guaranteed that.
So it's not a race.
But at the time you await, you're already launching the second thread, so you don't know how technically how long
Let me
it's going to
adjust the
take.
question then and say like... okay, fine. Yes, it's fine. So what can you say, where can you say with certainty, like I just like, where will it not appear before? That's the ordering, but putting aside the race problems, yes, it is after hello coroutine. It could show up after, as in after the other ones, I guess, yeah.
It could even be interleaved.
Sorry?
It could even be interleaved.
It's a,
Yes.
oh yeah, that's true because it's separate. Yeah, that's wow. Okay, I didn't think of that. But yeah, you guys are paying attention. Nice. But putting the messy stuff aside, it does come after a coroutine. Is anybody brave enough to tell me why it comes after? As in, at least why it's after, just after that line. As in, it could be anywhere after, but at least after that point. Yeah.
Because it's still in the main thread, so the thread ID would also be the same as the main thread.
Yeah.
So it'll just do everything that's in the main thread, like in order.
Yeah. So this part of the coroutine before the co-wait is happening in the main thread. So that bit has to run before we actually do the print line. And at which point, all bets are off. Anything could happen whenever, but at least this one is going to come out before the one in Maine. Okay. I did not think I'd be thrown off guard like that. Cool. So I guess I should prove it. Let's do that. Let's see the fun. It'd be really exciting if it does show up later.
Unlikely, because 200 milliseconds is a long time.
Sorry?
200 milliseconds is a long time.
I was tempted to make it longer, but then the demo would take longer to run as well. It's a trade-off between racing and speedy presentation. Oh yeah, so it finally shows up. Hello again from Maine, at least after. Yeah, hello from Coroutines, just in case you didn't believe me. Right, so some more fun questions. So what happens if let me take the whole thing first. I'm sure you can see the next question after this. So if I insert, let's do it here. What happens if I uncomment this line here? Take a moment to think about it, and I'll do the show of hands. My battery's going down. Is anyone brave enough to tell me what will change in the output? Or what might not, if not change? Yeah?
Well, suspend never just says carry on doing things, so nothing changes.
Correct, absolutely correct. Yes. So if you remember earlier I said suspend never is suspend never is a no-op, so the commented line might as well just stay commented, even if I uncomment it. So everything will proceed as normal. Next up, obvious question, I guess. If I take the suspend always and then insert it here. So let's say I uncomment this line of code. What do you reckon will change in the output? Have a think. Oh yeah.
So I think the last two lines disappear
Absolutely correct. Why?
because you're suspending at that point and never resuming it.
Yep, correct. Suspend always suspends the coroutine, and at no point here do I go out of my way to resume it after that point. So the last two lines disappear. I'll just comment that to show you that happening. But I think next time I'll just use a local IDE to just to run this. There we go, yeah. Last two lines disappear. That's the motivation. Just before I move on to the next demo, does anybody have any questions about anything I've shown so far, or anything that's not clear?
So coroutine and async is totally different. So async is more like a system behavior, and coroutine is more like a C++ behavior that kind of tries to emulate the behavior of async, but it really does not, because it doesn't have a runtime.
Yeah, pretty much. I mean, Coroutines is pretty much just about, well, at least the stackless kind, the kind we're working with here, is really just about creating a state machine at the end of the day. The async is something we kind of like put on top of it. It just turns out that orchestrating asynchronous work, you oftentimes kind of just need a state machine, and it's nice when you have this feature to make a state machine for you. So yeah, cplusplus coroutines is just about making state machines, and then we use those state machines to organize our asynchronous work. Yeah.
So how does it hold up to huge burst of traffic, but each traffic is IO dependent? Like async can do that because it can go back and forth in between different threads and can do that, like runtime scheduling and all this. So how coroutine works with that?
Well, strictly speaking, that's a sort of like a library problem. So I would expect like a async IO coroutine library to write something that scales well according to that if it's supporting that use case. But it's not like because it's two different, because all the coroutine does for you, all coroutines do for you is just a way to sort of orchestrate the states. It doesn't necessarily impede nor improve performance. All it really does is just help you organize it in a more easy to handle way. I suppose, or if you're worried about, say, like the overhead of allocations, that might be a valid one. Some people do worry about, like, oh, we're allocating a new promise type every single time you call a coroutine function, and if you're doing that for every request, maybe that like slows it down for some reason. There are ways to get rid of those allocations. One, we have like a Halo, which is, if I remember correctly, heap allocation elision optimization. Is where if the compiler is convinced that you're doing a very simple, like, you create the coroutine on the stack and then it's destroyed at the end of the scope and you don't move it elsewhere or do anything funny, it'll allocate the promise type on the stack rather than use new, and in which case you don't have to pay for the allocation. At the moment, last time I checked, which was a few months ago, so things might have changed now, the compilers are quite sensitive. So if only on the very specific circumstances will they actually perform this Halo optimization, and I think you have to do at least 03 to see it. You can also override you can sort of supply your own allocator. So if I'm only familiar with BDE, but if you create a sort of like a local buffer and have an allocator around it to kind of use that local buffer, you can then have your coroutines be allocated from that. And if you're making multiple, they can reuse that same space, so you're not paying for the allocation. But there's plenty of room to optimize that specific point. But besides the allocations, and I'm not really, I don't see any sort of obvious overhead from using coroutines to do to scale. I would say the scaling is a separate problem from coroutines, I'd say. I hope that somewhat vaguely answers your question. But yeah. Cool. Right, okay. Move on to the final demo. So this demo here, this is doing pretty much the same thing as the last one, except we're not spawning like 20 threads for every single sleep. So we have this my scheduler component. I don't want to focus too much on like what the implementation is, but high level, it owns a single thread. It's a J thread inside it, right? And it has a schedule method. This schedule method takes a delay and a function to run, right? So it just takes a copy of that function, well, not copy necessarily, but it takes that function and it promises to run it at some point in the future, at least after that delay. And it does that on a thread with a queue and things. But that's all you need to care about with regards to the scheduler. Single thread, and it organizes all the tasks into a queue and then runs them as the timers expire, right? I hope that's clear to everyone. That's simple. Cool. Okay. So now we have my sleep, which has been modified. So now it takes a reference to the scheduler and the constructor as well. And then await suspend, instead of making a new thread, we just ask the scheduler to schedule our handle to resume at some point in the future, right? So we're no longer doing detached threads. Now we're just using a scheduler, recycling that one J thread, right? My coroutine hasn't changed, so the same MVP coroutine that we know and love, that we keep changing its semantics for questions. And then we have a do something function, which takes a reference to the scheduler and passes it to all the sleeps. We're printing out the same thing here with the thread IDs, but I've also added a little Coro ID, which is just this little identifier. And then in main, print out from main, we make a scheduler, call do something with the scheduler, and then an ID for it. And then we sleep just to make sure everything completes because I'm too lazy to do that nicely. Cool, and then we have the output here, which is, the thread IDs are the same, 000, all as expected. Super easy question I'm gonna ask. So in my coroutine type, if I change initial suspend to return suspend always, how is the output gonna change? I would take a moment to think about it. It is an easy question, so no tricks. Just giving you a chance to answer a question if you feel like it. Okay, quick show of hands. Who thinks the output will change? Okay, who thinks the output will not change? Okay, if you think the output will change, you're correct, probably for the right reasons. Is anybody brave enough, who hasn't spoken already, but it's fine, brave enough to tell me why the output will change, or how it will change?
Sure.
Yeah.
You just stop at the beginning of the coroutine, just like all the other cases.
Yep, pretty much that. It is just the same boring answer as before, yeah. There's a call, wait, initial suspend here, suspends forever, when you change it, always suspend always, yeah. Same as always, just checking that you're paying attention. Yeah, cool. And then next question, another easy one, no tricks. So even though I have a scheduler, which is recycling the same thread for the sleeps, how come the thread ID, the first thread ID printed from the coroutine is different from the second thread ID? Another no tricks as well. Take a moment to think about it. All right, yep.
The hello from coroutine, the first one is happening to the same thread as the main thread, and then the others are happening in that new scheduler thread.
Correct, yes. The first bit happens in main, and it's only until the co-wait sleep is the scheduler actually used. So that's where the thread IDs are different. Yeah, similar as the previous demo. If it sounds like repetitive, it is. It's just a simple question just to keep you on your on your toes. Cool. Now we're getting to the final question. So what do we think will happen if I uncomment this line here, 142, with do something with 1? How do we think the output would change? Take some time to think about it. Or just raise your hand now if you're super confident. Yes?
It'll be like hello from main, hello from coroutine 0, hello from coroutine 1, and then the hello again from coroutines will kind of probably be interspersed.
Yeah, correct. They'll be interleaved. So initially when I planned this question, I was going to say it's going to be 010101, but after the last demo with you guys calling me out on my race conditions, I'm not going to make that statement. But yes, they will be interleaved somewhat. But yeah, let me just quickly show you that. Which will take a few moments. Voila, yeah, okay. So yeah, here we have multiple coroutines running concurrently, and their outputs are interleaved. So yeah, we see the printer from main, then we see the first coroutine we ran, the second one, and then the remaining come out. Yeah, and then the same thing will happen if I comment this, but that's not too interesting, I have more output. Let's see, what other was I also going to ask about this? That's been handled.
So I think it's actually guaranteed to be 010101.
Oh, I'm curious why. Yeah.
Because all of those coroutines are running in a single thread.
Yes.
And so the time will increment each time will be greater than the previous one.
Yeah, that's correct. Yeah.
There's only a slight race against main, which you have 200 milliseconds.
Right. That's true. Yeah. Yeah, that sounds right to me.
Are there performance issues in like different threads? Like I don't know.
Sorry?
Could there be other differences in performances in the different threads, like other than the 200 milliseconds? Like could there be some additional overhead due? I don't know. Because of that, there could be more interleaving.
I couldn't answer off the top of my head, if I'm being honest, at the moment. Yeah, not on the spot.
So the initial times at which they're inserted will be increasing unless you have a pretty ungranular clock.
Yeah, I mean, here I'm using a what is it? Steady clock, which I think is the monotonic one? I think.
Yes, steady clock is monotonic.
Yeah. Okay. Yeah. So it should be guaranteed to be interleaved. I can't think of why it wouldn't be, but Yeah, definitely on the spot now while I'm being recorded in a presentation. There was one
And
final
it's
thing.
usually reasonably high resolution too.
Yeah. I haven't read it too deeply. Right, coroutines is leaving. Yeah, okay, that's it for that demo. That's the last demo. So this is it for the part 1 of this series. Part 2, 3, and 4 go into more detail about, for example, I've only shown you like singular coroutine functions. In practice, you also want to see how these coroutine functions call each other and co-weight each other. You just be doing them in practice. That's a sort of part 3 thing. Hopefully one day I can maybe present it now at a different conference, I don't know. But yeah, hopefully this was useful. If you weren't familiar with coroutines before, maybe now you have more insight. Maybe I've cracked the code for you, perhaps. My battery's going to die soon, so I'm not going to show you much more. But that's it. 1 second. I have something to show. Yeah, thank you for listening. Any final questions before? I think we have 4 minutes left. Oh yeah.
Is there just so high level is fine. Like I know you mentioned like sometimes you want to use that final suspend always. When when would you use that?
Right. So okay. I'm trying to remember the semantics here. Oh, Dietmar, can you help me?
I can help a little bit.
Yeah.
So in the sender setup, actually, I need to destroy the coroutine frame at some point, but I also need to get hold of the value. So in the final suspend, by suspending over there and keeping this alive, lets me hold on to the coroutine handle long enough after the coroutine is done, so that I can steal the values.
Right, and then suspend it.
And then explicitly release the single.
Yeah, that's the main use case. There's a second one for generators because if you use suspend always, you can just kind of unconditionally free the coroutine at the end when the generator finishes, as opposed to checking to see if it got to the end versus if it stopped somewhere in between or something like that. But sorry, you were about to ask a question.
I was just going. So to get the coroutine that was to clean it up afterwards, you would still not use suspend always. You would want to use something that would capture the coroutine handle, right?
Yeah, so there will be something that would have the handle and then call handle.destroy in it. So it'll be, typically you would expect the 8%, okay, I can still show you. Where's the, yes, get return object. So here, since we're inside the promise type, here, we actually have access to, I'm showing you the API. But from inside this function call, we're able to get the coroutine handle of the coroutine, and we can then pass it to the constructor of my coroutine, right? Then in the destructor of my coroutine, we can then explicitly call destroy on the handle, right? But that is how you would typically do it. So final suspend will be suspend always. You would get the handle stored in the return objects through here, and then in the destructor of my coroutine, you would call destroy on the handle. That's how you do the cleanup. Yeah. Just switch back to slideshow mode. Okay. Any more questions? Yeah.
You mentioned a coroutine library a couple of times, and so if I wanted to use coroutines today and I didn't want to write in Waveable, what's your recommendation?
Okay, it's an easy one. So in C++26, we have an STD task coming, which has been proposed by Dietmar, yes. So I would say wait for that. Okay.
Well, if you want to do it now.
Now, so you said now, yes, that defeats the point.
Tricky, right? So,
we have a Beeman, is this a...
yeah, you could use it from Beeman. I wouldn't claim it's production ready, it's not classified as that. Folly, like the library shipping from Facebook, they have coroutine stuff. I think Folly is probably the most stable, most yeah,
Production ready.
maintained one I'm aware of right away. It's not looking how the standard level is going to look like.
Sure.
These are the two options. Yeah, I think my batch is about to call it quits. So yeah, thank you. I'll stop here.